Hello everyone. Today I'll present the spin-based data storage chapter of the Comprehensive Nanoscience and Technology book. So in this chapter, we'll mainly talk about the new phenomena that emerges in the submicron scale and structures called as nanomagnetism. This phenomenon, nanomagnetism mechanisms, has been topic to many of the subfields, but here the main topic is data storage. So potential benefits of utilizing the spin degrees of freedom in storage devices are non-volatility, more efficient power consumption, improved data processing speed, and high integration density. Actually, I'm saying these at the beginning to emphasize you that this nanomagnetism, when applied to data storage devices, is seen to be very promising. I think the most important part here may be the non-volatility, because you don't have to supply power to maintain the configuration of the system. So we will go briefly in the beginning, and then we will deeply investigate. So, okay, our motivation is to make storage devices, and mainly the storage devices should have 4 operations: write operation, retention, transport, and read operations. Okay, read operations. Okay, excuse me. In the spin systems, write operation basically is the manipulation and the change of the spin system. Retention is basically the maintaining the spin system. Transport is just basically transport, and read operation will be the detection of the configuration of the spin system. So we just model a magnetic bit as a macrospin system, which has interactions with the environment and which causes different sort of torques. First, we may say precessional torque. This is constructed by effective magnetic fields, which can also be observed from thermal fields, applied field, magnetic coupling, and these certain detailed structures and manipulations in the ferromagnets and antiferromagnets. I think the more interesting will be on the ferromagnetic oscillatory exchange dipolar coupling. I have a good video explaining these all of the effects. So I'm going basically on this figure now. Damping torque, which comes from the lattice interactions of the material, and we have spin torque coming from the electrical current. So just move on. We have a video telling ferromagnetism, and also spin waves, but this is not the topic of our today. So, okay, we have a figure illustrating the atom, and the arrow just points the direction of the spin of the atom. So when we have a multiple system of the atomic configurations, in the paramagnetic materials, these are just randomly fluctuation orientations. And when we apply magnetic fields, these orientations just move through a direction. And we see here in the right graph that magnetization comes to a saturation point when we apply a magnetic field. This is just basically the precessional torque that I was talking about in the figure. So yes, and we just take the field, and they go back to randomly oriented ways. So if we take 2 neighbor spins, we see that they also have tendency to affect themselves, and which is called ferromagnetic interaction. And if we go deeply in observing that, we see that they tend to align. Okay. And if we want to designate how the operations are going in the microspin system, we see that in ferromagnets, all spins affect each other. And the high temperature, these are basically random fluctuations, random interactions. But if we cool down our system, we see that they tend to align and affect each other, but not picking any direction. If we move on to cool down, we see that from a certain temperature, critical temperature here, they tend to align to one direction, and we see that they act as a permanent magnet. And from going on, if we cool more and more, we see that they tend to have a certain degree of magnetization. Okay, this was basically the act of ferromagnets, and we'll see that we will benefit from these effects so much in these storage devices. So here we begin our journey with right operation. Right operation is basically, we're talking about macrospin systems, and just probabilistic nature here we see in the right operation. So we can think of right operation as here we see in the A figure double well structure here, and the atom just is trapped to a one well. Right operation is basically by applying a magnetic field, we make the atom pass from one well to other. So this is inherently possesses the retention qualification of this system, because here is the anisotropy energy designates our systems like energy to being able to change the system. So this is just satisfies the maintain operation. Okay, I think we am I going a little fast, or is everything okay? I guess it's okay. So I'm going on. Okay, our third thing will be the transport. So we will see spin-dependent transport in magnetic nanostructures, which will include three subtitles: spin filtering, giant magnetoresistance, and spin transfer switching. So spin filtering, well, I said that magnets will be important here. In ferromagnets, we see non-symmetric density of states versus energy graphs. Well, actually, this will cause imbalance and exchange split. Here, when a ferromagnet is when a ferromagnet is brought together with a normal metal, we see the band mismatches, which then leads to spin polarized currents. And in the giant magnetoresistance, I want to first start with the question that arises giant magnetoresistance. The question was, is electrical current affected by the pole directions in thin magnetic layers? Okay, so they went through the lab and gathered some results. Okay, you see here in this graph, we have two magnetic poles. When they are directed anti-parallel in the beginning, you see in the magnetic field 0 here, we see a greater resistance, and when they are aligned in parallel, we see that resistance just goes down. I have also a video explaining that, so you just we may watch it. Okay, this results as made Albert Fert won Nobel Prize in 2007. Okay, here's our graph, resistance versus effective magnetic field. Okay, here the bilayer system. When we make current pass, the spins with the designated orientation pass easily, and when they confront the other-sided magnetization, they just can't pass. So this anti-parallel system is where resistance is in the greatest. So we slightly change the magnetic direction of one layer in time. So here we see that nearly all electrons, they are in the same direction, could pass easily, and which makes us to have much weaker resistance. Okay, this is basically our graph. All right, so I can keep going on. So here, as we saw, we have a fixed layer and we have a free layer. So with the relative orientation of magnetizations, we obtain different resistance. So this structure is called spin valve. I want you to remember this because in the next step we will see that if we fix the free space space layers, we will get another magnetization results. So okay, giant magnetism resistance. Oh, okay. One problem that we here encounter is we want a fixed layer in the lower side. So how do we obtain a fixed layer? We can just use we can use different types of materials, different types of layers to obtain SAF, which is called synthetic antiferromagnet structure, to obtain a fixed layer. Here you can see the pinning layer, antiferromagnet pinned with a magnetic layer, which causes strong mismatches. Because of that, high coercivity is obtained, so it's difficult to change the orientation in this layer. So we can just call it as a fixed layer. All right, tunneling magnetoresistance. In this magnetoresistance type, we have 3 ferromagnets and an insulator tunnel barrier in between. So we just switch the non-magnetic metal spacer in the previous header we see. Okay, and this structure is called magnetic tunnel junction. So okay, another spin transfer topic is spin transfer switching, which is observed in the pseudo spin valve structure. Here in this structure, we just mainly have 2 layers of the same ferromagnet, but one layer is the thicker one, which is then act as a fixed layer, right? So when we flow the electron, you see here in the electron flow arrow from fixed layer to free layer, the spin orientations are transmitted in the spacer, then causes precessional torques in the free layer, which then effectively changes the orientation. In the opposite sense, when we give the current from free layer to fixed layer, this is exactly the inverse magnetoresistance effect. The spin orientations coming here just are reflected from fixed layer, you see, and then they just like go and come back, and the effect is also the precessional torque effect. Okay, switching. All right, we just talked about right operation. We see that it's inherent the retention because of the double valves and the transport system that we have. So the next episode will be read operation. So the basically most common used read head sensors will be magnetic tunnel junctions, which benefit from tunnel magnetoresistance. So here in the left, we see a hysteresis loop. You see that in that one axis we have applied fields and the resistance or or area. So here in the parallel systems, when we apply a magnetic field, constantly increasing magnetic field, from a certain point on, we see that the resistance just goes up. Okay, and the inversely, we just decrease the applied field, and from a certain level in the here anti-parallel high resistance level, we see the same resistance, and then just drops down. Okay, in the right figures we see anti-parallel and parallel orientation. Here in the parallel one, we see that the high probability of the electrons spinning on the same orientation has the ability to go between the ups here in the downspin, for example. So we see a high probability of finding the electrons in the low spins that because of the tunneling effect, but this is not observed in anti-parallel one because we just have the opposite directions of the spinnings. Okay, I can go on. Oh yes, here these figures illustrate the many bit systems you see in the bit and bit resistances. Because we are basically talking about probabilistic finding probabilistically states to be found, we see we should see a reasonable amount of differences in the low state and high state finding probabilities to be able to detect the current situation of the system. Okay, so we just basically yes, we talked about read operations here too. So we go on magnetic random access memory types. We have three types of memories: conventional field switch, toggle switch MRM, and spin torque MRM. This will be basically the applications of these properties that we have I have mentioned earlier. So we see here conventional field switch MRM. We just have a magnetic tunnel junction with a fixed layer in the bottom and then free layer at the top. We here see two axes. Actually, one is oriented towards the hard axis and other for the easy axis field. Well, what here hard axis field does is it makes it easier for us to switch the upper layer, easy axis field. This is well declared here. Okay, in the free layer magnetization, we have a right arrow here, about it's 0, and the upper direction, this shows the hard axis field applied current, and magnetization goes here and up, and which is just prepares for us to be able to change easily when we applied easy axis field. You see here the left arrow designates that effect, and just when we took both of turn currents both off, we see that we have changed the direction of magnetization. Well, actually, these currents are given simultaneously, which makes us possible to draw this figure here. So we see hard axis. When we have hard axis field applied, it's more easier for us to change the direction here. All right. Problems that we encountered in this configuration is here you see on the left side we have an array of magnetic cells. So we just want to store the information in these cells. So here you see the selected bit, we want to change the orientation of basically the information that we keep. So we give the two I1 and I2 as you see, but this causes a problem which is called half select problem. When we give I1 here, for example, we just affect the other cells too that we don't want to change. And because of the random fluctuations, we told that thermal effects also cause precessional torque, and that may cause the deorientations that we do not want. This problem is actually a really serious one. As you may see in the right figure, because of this problem, we just have an operating region very narrow, and as we make wider arrays of cells, this operation region shrinks. So this is the one problem that we should actually overcome. So here, toggle switch MRN. So I want you to remember the SAF, synthetic antiferromagnet free layer, which was the antiferromagnet basically pinned to free ferromagnets. This profit makes here we can follow this left figure here. Here in the first one we have an anti-parallel alignments of the lower and the upper states. The most important part here is that in the previous one we have just one free layer on the top and a fixed layer at the bottom, but here we have two layers that we are about to switch, so which makes us a little bit more secure to prevent the half selected bits problem here. So okay, fixed layers, we see fixed layers, anti-parallel alignment here. When we give the first current, okay, we see that we just change the orientation 45-degree here, which provides a stable orientation. So it's more difficult for the fluctuations to cause any changes in the overall orientation. So here we go, we applied free axis 2. We just have both 45 degrees. So when we leave one side current and the other side, you see as that they are just aligned the opposite sides. So here on the right, we have the figure of operating region and switching region. You can clearly see the result is obtained. Result obtains better here in the operating region surfaces. Okay. Toggle switch was our second, and third is the spin torque MRAM. The most important aspect of spin torque MRAM is that we just have two layers, three layer, fixed layer. Remember, three layer was the thinner one. Fixed layer is fixed because it's more thicker layer. So we just giving one current. We do not have the hard axis and free axis, easy axis, because of the one's axis current. It is more cheaper and more easier for us to change the direction of the layers. But the real problem here is that we just don't want to have dielectric breakdown, while actually it's occurred in nearly every aspect of the tunnel junctions too. But here, because it's the more precise and slightly narrower sense that we control the layers, we should really be aware of the applied voltage for the read and the switch and breakdown operations. Okay, and finally we have a table showing the comparison to conventional memories. Here the toggle MRAM, spin torque MRAM, flashes, DRAM, SRAM. Well, when I first looked at this table, I saw here that read times of SRAMs are really low, but the main importance because of this magnetic memories that the gain is non-volatility, and this is actually a trade-off between them. But overall of all, we see that the MRAM devices really do actually good for our devices. Okay, all right. Here the sources that I've used, and thank you for listening and your time and your attention.